Sorry? I can make them available. Yeah, I can make them available. Yeah, they're public, so maybe we can work this out with the Eclipse folks afterwards. Maybe we can work it out with the Eclipse folks a little bit later in the day and see how we can make them available to you. Yeah. All right. I think we're all set. Okay, wow, lots of people here today. I'm a little bit nervous, but I really shouldn't be because I've been doing this for quite some time, and I've been giving this presentation for several times before, and it only gets more and more exciting every single time I do it. These are some really amazing projects, and I'm going to tell you all about them today. My name is Sudhir Panu, and I am an IoT software architect with Intel Corporation. And nowadays, I really work on developer tools for the most part, as well as application development for IoT, AI, and computer vision. Well, you know, at Intel, you get to wear a lot of hats, I would say. So many hats that sometimes when I open the closet, like, they fumble on me. It's like, hey, look, it's my Fedora hat, but today it's Ubuntu Day, so it doesn't work. Let me get to the agenda first and tell you a little bit about what I want to talk to you. I'm going to do a quick introduction and tell you about the projects, how they came about. Then I'm going to give you some very high-level details about them. I'll go do a deep dive afterwards, and then I'll give you the big picture. So how do the projects integrate into with other tools within the IoT ecosystem and so forth. To wrap it up, I'll talk a little bit about industrial standards, interoperability with other frameworks, as well as some future plans under Eclipse for these projects, because they are becoming part of the Eclipse IoT Foundation now. So why sensor framework? You know, I joined the project, it was back in 2014, 2015. And I wasn't there on the first day. I actually, two of my colleagues, Ajay Mungara and Brendan Lefol. Ajay was more of a marketing engineer, and Brendan, the architect for the projects at the time. They were sitting in a bar, and you know, Intel back then had 3 developer boards: the Intel Galileo, the Galileo Gen 2, and the Intel Edison. And they were taking them to show them to developers, and they were having a difficult time, like programming them and you know, connecting things to them and sensors, and because it just takes a lot of steps to do that. So as they were sitting down in this pub, they were like, okay, well, what can we do about this? Well, let's come up with a hardware abstraction, and let's do it in a way that nobody has done it before. Let's do it in a way that's portable across platforms, it works across multiple architectures, it works across OSs and so forth. And Brendan was here, but Ajay, this is nuts. I mean, it's just not gonna work. It's a pet project, right? And it kind of like started like that, but you know, it actually did work. And it actually worked so well to the point that if you combine the MRAA and UPM projects, you get so much hardware abstraction to the point where you can get to your sensor data with just a few function calls. And that's really, really important. You have a constructor for your sensor, you initialize it, you configure it once, and that's it. From there, you make a function call, and you get your sensor data. So let's see what MRAA does. MRAA is more about the hardware abstraction, right? And it provides abstraction APIs for basic pins and buses that you would have on a typical edge device. For instance, GPIOs, analog pins, PWM, and then a couple of buses like I2C, SPI, serial, and a few other special purpose maybe things here, like one wire for MATA, IO. We also have some LED APIs for some of our boards. And the boards, I have them at the bottom of the slide. Lately, we've been working a lot more with Eon, things like the Up and their Up-squared board, as well as some of their kits, and more recently, the Up Core Plus, AI Plus kits, as well as a couple of Intel entry workstation and server platforms. So they do span across, pretty much all the way from the edge to gateways and more powerful devices. I guess Frederick was showing you earlier the slide with MRAA and UPM being abstraction layers for the edge, but really they do go beyond that as well. You can use them on more powerful systems, and I'll get into that as we move along. The UPM project complements the MRAA project and goes even further up the stack. So, you start with the Linux kernel. That's where everything happens, right? That's where you do device access and everything. You work with the hardware, but then how do you get to that from a user space, right? MRAA puts those buses out there for you, but that alone is not enough because a lot of the sensors are complex devices. You have to, just to configure them, again, you have to go through 10, 20 steps, and then you have to simplify that for a developer so that they can get meaningful data. And this is really what we wanted to do with UPM. We wanted to give you meaningful data out of the sensors, easy way to control actuators, and then we kind of like spread out to support connectivity options as well as some industrial options. And we try to standardize all this in the way too. And what I mean by standardizing that, interfaces that provide the same way to access a sensor, be it from one vendor or another. Usually the functions are going to be the same, and you can just migrate your application if you want to later on. After you develop it, you can change the hardware, swap it out, and not have to rewrite almost any code at all. So about this value proposition, I'm saying here 400 plus specialized sensor drivers, and these are the cool sensors, right? Because theoretically, we support thousands, if not tens of thousands of devices. You could go to websites like Mouser, Arrow, DigiKey, whatever, buy switches, LEDs, and whatnot. They all work. Like MRAA will allow you to toggle those LEDs or read the values on those switches fairly easily. However, the more complicated sensors, and that's where we started with some of our prototyping partners, or I could call them prototyping partners, but there are companies that make affordable sensors. Let's put it that way. Sensors that you would use, to prototype a device. But then, what about the industrial-ready sensors? Well, we support some of those too. And we partner with companies like Omron, Siemens, Honeywell, and these are just examples, of companies that have contributed to the projects in some way or form. And others, Maxim, ST Micro, Semtech, so forth. And for connectivity, we actually have a bunch of options as well. Both wired and wireless. It really depends on the industry. So for instance, if you were to deploy a solution in automotive, you would maybe tend towards a CAN bus, and we do support some of those radios. Some of those controllers. But then if you wanted to go over the radios, you could do things like LoRa, Zigbee, wireless, of course, and others. So let's move a little bit more into the ecosystem and how you can get these libraries. Well, there's multiple OS support, and what I mean by that is not that you can just grab the code and build it and have it working on that OS, but really for a lot of these we have native distribution channels. So you can get them as packages for that system. On Ubuntu, you can just do apt install MRAA, and that's it. You get the library, apt install UPM, and you get the 400 plus sensors, sensor libraries, and it's 100 megabytes of sensors, but you can trim them down later if you want to. When you start out and when you're prototyping, you're developing, you don't care as much. It's about ease of access, right? So as you're looking at the OS list, you're like, hey, you do have two things in there that kind of like stand out, right? Over to the far left side, there's Zephyr. Zephyr is a real-time OS, and we support that as well. MRAA UPM do have, let's call them sister projects, sub-projects, something like that. There's a spin-off of the libraries that allow you to work on Zephyr if you want to. The Octo project, you know, I don't even have to mention that with partners like Wind River and whatnot. Clear Linux, which is another Intel initiative, natively supported as well. Debian flavors, Ubuntu's there up on the list, but then, you know, from guys like Eon, we support UBLinux as well, and that's one of the OSs of choice for those up and up squared platforms and those series. And then the community added more. They added packages for Arch Linux, Fedora, and even Android things, and that was quite impressive. It's not Android per se, but Android things was this Google initiative to, you know, enable developers at the edge. And through the use of our Java bindings, we were able to enable them as well. So you heard me say Java bindings. Well, what do I mean by that? The projects are natively written in C and C++. So that's fairly common. You know, when you need hardware access that's fast and quick, you do it in C, right? However, how do you handle all the other languages, right? We chose to use a project called Swig from simple wrapper and interface generator. So what it does, it can translate one language to the other. You know, there's some formal grammars involved and stuff like that, but the resulting code is pretty good. It's functional, and it can be cleaned up as well. You can specify, you know, exactly what happens to the data structures, because there are always going to be issues between, you know, strongly typed languages and interpreters and things like that, loosely typed languages, but you can make it work. And with the examples and the sensors that we have in the UPM library, you'll see that, you know, a Python developer might say, it doesn't quite feel 100%, but it's functional enough to where I can actually write a pretty decent application and use this. So the other languages, Java, Node, Python, well, Node is actually JavaScript, right? But we used to work a lot with the Node platform. And then we also have Lua and Go. Those are community contributed as well. They're not available, let's say, with the main projects per se, but there are ways to get to them if you want to use them. The code itself, available on GitHub, all open source. It has been open source since day one. And then we have some IDE integrations as well. The main ones that I would actually call deeper integrations would be with Arduino Create, which is a web-based IDE, as well as Intel's own System Studio, which is based on Eclipse CDT. So moving on, let me show you, or let me tell you a little bit about our infrastructure and how we test the project. So we've automated a lot of this to the point where, you know, whenever somebody makes a change or wants to make a contribution to the process, it kicks off builds with multiple compilers. It tests, hey, did you add an example for your sensor? Is it there? And all that stuff that happens automatically. And all that's a part of Travis CI. And we use Docker builders. So Docker offers this really flexible solution for us, and it was very easy. We also make those available either as Docker files. You can get those from GitHub if you want to. And basically, you build that, and you just get the same environment or same tool chain that we use in our own CI systems to build and test the library. So it's all there. You're ready to go just by, you know, getting one of those Docker files. You can also get the binaries if you want, like through Docker Hub, you can get them as images right away. For bugs and security vulnerabilities, other things like that, we put things through Sonar Cloud. Right now, the projects have 0 vulnerabilities, tons of bugs, as you can see from this slide. They're not all, you know, true bugs. Like a lot of them, we're in the embedded space, you know, but then Sonar Cloud will say, oh, 100 of these bugs are because your loops are infinite in the examples. I'm like, well, but it's embedded. It's just going to run forever, right? So things like those. But and they're usually hard to not hard, I mean, pretty easy to clean up. We've done it time and time in the past, so we do maintain the projects actively. Sonar has this thing called quality gate, and it shows failed on both projects right now, but that's because of the new contributions, right? Because as you merge new code into the projects, like it takes a little bit of time to refine that and put it into a usable state. You want to merge it in soon because you want to make it available for other developers, but it takes a little bit of time to get refined. So how far do these projects go? Well, with MRAA, I can give you some example contributions, bug fixes, and other samples that were added to the projects from guys like Arduino, Siemens, Linaro, ARM community, which is really, really active with the project. They've added basically all their 96 boards to the project, and they use them actively as well. Apple, SAP, Amazon, Microsoft, other cloud service providers and partners. We actually develop kits with them at times. Like for instance, the RFP kits, request for proposal kits. So that's when, you know, a OEM, ODM comes to Intel and they say, oh, we have an idea, we want to build this product, put it out in the market, but we don't exactly know how, where to start, and we don't have the right contacts, things like those. We can help there. We also integrate with the reference OSs, like Wind River Linux and Clara Linux. And you know, the sample external usage, basically that list is pretty huge. From STMicro to GE, Qualcomm, Honeywell, Siemens, Omron, and others as well. We had new boards and new developer kits come out, and without even talking to the guys behind them, we found out that they found out about our projects, and they've added their support for their boards and the sensors that came by default with the board as well. And they found it really easy to do so as well. So contributing to the projects is not difficult at all. They are offered under the MIT license, and that's very, very specific and very important as well, because what that means is that you can basically do whatever you want with them. So you can take the projects, you know, I think that most of the people here in the room are all about open source software, right? But sometimes you also have to like make some money and sell things. So if you wanted to like, you know, turn this into a product, you could do that too. About authorship and who contributed to the project. You know, this is no surprise here on this slide. There's a lot of blue in those charts, right? And that's because these were Intel started projects. But, you know, others contributed quite a bit. And you can see that better on the MRAA project, where, you know, only about 75% was Intel copyrighted, but then others added in code too. Not everybody adds that, so like, you know, smaller contributions, bug fixes, like usually you don't get to put a copyright on a file. But, and some people contributed to the project and, you know, used the Intel copyright for that, so, you know, that's fine too. Of course, we would not refuse a contribution just for that alone. And others decided to keep their own copyright. So that's perfectly fine, as long as the licensing is usually not conflicting, things are good to go. Going back to that IDE integration, I was calling out the deep integration with the IDEs. This is really where the projects start, you know, making sense, because this is where this is your toolbox, right? This is your development environment. This is what you work with on a day-by-day basis, because the IDEs themselves, you get the debugger, you get everything else, you know, that allows you to actually write code and make sure that it works the way you want it to. For Arduino Create, you can use the sensors right away. You can add them as an external library. For System Studio, we have a thing called the Sensor Explorer, but I'll let my colleague Anjali speak about that more in the upcoming talk. So please stay around and listen to that too. So how about for industrial partners? We have this also, we also have this thing called the sensor catalog template. Or basically it's a UPM website in the sense that it shows you a collection of all the sensors that are in UPM. It's fully open source as well. You can get the code to this website. It lists all the sensors. You can filter by connection type. You can filter by manufacturer. You can filter by, the type of the sensor. Is it a temperature sensor, humidity, proximity sensor? You can add all those filters. If you want to break this down and like remove part of the sensors, and let's say, I don't know, you want to work with just some specific OEMs and ODMs and just keep like 50 of the 400 sensors, you could do that too. And then you can customize the template, to make it feasible for the partner you're working with. From that, I'll move into standards and compliance, because these are what drive real products and compliance. So we looked at it, and we looked at it really hard, because sensors and actuators are not new. We started the projects in 2014, and as I said, things were here and there, but not as centralized as the MRAA UPM libraries made it. And then we looked at the standards. Those were out there already too, well-defined. Things like OPC Foundation, right? It drives a lot, especially in the gas and energy industry. We do support it and have some examples of how you can write both client and the server side implementation around OPC UA. We picked the Open 62541 library for that, but you could integrate with other frameworks that support OPC UA as well. Other standards we considered something around CoAP, maybe like Open Connectivity Foundation and IoTivity. That was the project there. We have some examples of integration too, and we've been considering Dell's EdgeX Foundry too, which, by the time we did this part of research, it was still fairly new. So EdgeX was just starting out back then, but I did follow up with the projects, and it's a pretty hot one right now. So the key takeaway from this slide would be that UPM complements the standards really well. And what I mean by this is that you can take that sensor data I was telling you about, you make one function call, you get the sensor data. And from there, you can plug it into one of these standards or templates. In some cases, we even provide utility libraries, like with OPC UA. There are some extra things you could do, to facilitate putting the sensor data in the right format to match that standard. It's not always there because, with these standards, like they define their own sensor types and whatnot, and a lot of times you'll have to build a device that's highly custom. So that data that you pull out of the device, you'll have to mangle that a little bit in one way or another, and then push it back into the standard. So sometimes the developer will have to create that link themselves, but they do complement each other very well. So moving towards the more powerful edge, which is a trend that we see nowadays, and we just saw some examples about how you could use vision at the edge. So Intel also provides this thing called the OpenVINO toolkit, and this is all about computer vision, running inference, detecting things, basically anything, including hard hats and vests. And UPM complements these very well too. Why? Well, you have a camera and you have a framework for doing inference, recognizing what's in the picture, but who's going to move that camera around? Who's going to point it, but change the focus on the lens to make sure that you can actually see what's going on? How are you going to trigger, let's say if you detect a person walking up to a door and you know who they are, you want to open the door for them automatically. You got to trigger like a coil or something. You can do that too. Like if you want to provide feedback, like LEDs, something lighting up for a user to let them know that an action is happening, UPM and MRAA would fit right in. And then you can easily complement, these vision developer kits with what UPM provides for motor control, distance measurements, things like that, motion detectors, light sensors. And we actually have quite a few demos that show you how you can do that too. From here, I'm actually going to take this even further. I'm going to say, all that vision is cool, but then what else can we do with it? Well, how about FPGAs and accelerators? And the story I'm trying to build around this is that, well, first off, MRAA does work with FPGAs. We do have this developer board called the D10 Nano. It's a little bit older, but MRAA supports it very well. That's actually an ARM with a Cyclone 5 FPGA right next to it. And then you can easily take that and scale it up. So you could support other FPGAs that are available, and they are usually exposed as sub-platforms from the MRAA library. So think of sub-platforms as extensions to the MRAA library, so it's something that's not necessarily on the device that you support itself, but like an add-on, right? That would be a good word for it. You can also mix and match x86, ARM, and FPGAs, as I was saying. And the best part is you could use them for traditional I/O expansion and doing level shifting and whatnot, making sure that you have enough outputs to drive all your sensors. But you can also do sensor fusion. And I think this is going to be really cool because sensor fusion is really where we're going. Because we all know, like for instance, take the examples of self-driving autonomous cars, right? You can't just do it with sonar. You can't just do it with radar or LiDAR. I mean, even Elon himself said like, oh, LiDAR is too expensive. Let's just do radar. And you can't just do it with cameras. You have to combine the information you get from all three, right? And then you actually have a good situational awareness, and you start to understand, the picture around you and how that works. Another thing you could look at is the compute stick. This is essentially a neural network accelerator, I would call it. So this would work for both vision, for inferencing, but you could also do natural language processing, right? So if you wanted to do audio processing, that works fine. And you could use it for more. Those are just the examples that you see everywhere. A lot of companies and industries already use these for things like haptics. And you have your phone on you as you walk, your Fitbit, your wearables. Like you can actually aggregate all that data that you get from your users and then accelerate them with devices like this. And you can use it on any board too. You can take the compute stick and put it into a Raspberry Pi if you want to, and you can run OpenVINO there and do inferencing, and the projects, even though they're made by Intel, would still run on that platform very well, because this is about being open source and being cross-platform, and it's Intel software. It doesn't necessarily have to be x86. So here's a diagram with some proposed future development under Eclipse. The text might be a little bit small, but I'll try my best to talk to it. So for the MRAA library, I'll start with that because that's the middleware level. And a little bit simpler. It's easier, like it's a smaller library. It only has about 30,000 lines of code. We're in the process of transferring that to Eclipse. The Eclipse IP team started reviewing the code in the library, making sure that all the licenses check out and everything is good. We've added, and we're starting to improve support for mocking sensors. So what does that mean? Well, let's say I want to run or build an application around sensors without having the sensors. I want to do this on a container, in a virtualized environment. That's what the mock platform would do. It would generate some random sensor data for you to look at and use. Of course, other things, at least on the Intel side, we will be supporting upcoming developer kits. And those are going to be, both for IoT and in the client area as well. As I was saying, these frameworks work real well at the edge, but you don't have to limit yourself to using them at the edge. You can take them out of the edge very well, go into fog computing, and go into gateways, maybe not cloud, but I mean, if you wanted to virtualize, and do something like that, you could. Let's say if you're a cloud developer and you want to prototype how you would be aggregating the data and how you would doing your map reduces, whatnot, I don't know, then you could definitely do it with the MRAA project and the mock platform. And another thing on the list, this is later in the year, hopefully we can enhance a little bit on the I/O support for FPGA devices. We have some really good proofs of concepts right now with Cyclone 5 FPGA, but you could scale, up or down to either Max 10, which is more traditionally used for I/O, but then you could also move up to ARIA and Stratix. For UPM, we're actually looking at adding some PLC support, and that's actually with our partners at Siemens. They came up with this IoT 2000, IoT 2020 platform that's really, based on one of those Galileo boards, but it acts as a PLC. It runs the Octo project with a real-time kernel. You could do command and control with those for industrial systems very, very easily. Also, we just released the 2.0 version of UPM. That's a major stable version. Includes a lot of interfaces and other things that just happened a couple of days back. And of course, the project is also in process of being reviewed by the Eclipse Foundation. Let's see, what else do we have for UPM? We do want to add a little bit, or we want to add additional interfaces for radios and the communication devices that we support. OPC UA, we want to enhance that integration, and we also want to add additional interfaces for actuators. And the community seemed really interested in that. Like the interfaces, the 30+ interfaces that were just added with UPM 2.0 right now, they're mostly for sensors. So you get the humidity, temperature, proximity, whatnot. But then what about a stepper motor? How do I drive that in a way that works across all the stepper motors, regardless of what controller you have to drive them and all that. And closing up here, I just wanted to show you the upcoming conference, virtual conference that I happen to be a part of, called Intel Global IoT Dev Fest. I used to not do this, but then all the examples that I had throughout my life in other presentations, my advisors and whatnot, they would always use the last slide to show something, a cool event that is coming up. And this is going to happen in June 18-19. Registration is absolutely free. It spans across all the time zones, 2 days of nonstop talks, 4 conference tracks, and it's all based around AI and going in production with AI, because this is really where the future is heading with the sensors and these projects. You start at the edge, but then once you get that data, and crunching that data becomes a big challenge, right? And this will show you how you can deal with some of those challenges. And this pretty much wraps it up. This was my talk for today. Seems like we will have some time for questions and answers right now during the session.
Any questions at this time? Well, I have one personally. That's not necessarily your domain, but I'm curious about it. So back in the days, I really loved the Intel Edison boards, working with that, and I miss them. So will you at some point re-enter somehow that market, or are you gone completely and focusing on edge nodes rather than smaller devices?
That's a really good question. That actually a lot of people got upset when the boards got pulled off. And a lot of people said that Intel did it too early, and I tend to agree with that, because you can't build trust that way. But the truth is that Intel really never moved away from that. It's just that it's partners that are now building the boards. But that was the main difference. Those were reference boards that were built in-house. We showed those to the world. The world loved it, but then others, OEMs, ODMs, picked it up. So it's like the IoT 2000 platform I was telling you about from Siemens. That's a really good example of how you could take one of those boards, the Galileo, turn it into a real product. Of course, it's only going to happen 3-4 years later. Why? Because you have to go, from the actual sketch that you put on paper and turning it into a real product into the industry takes years, right? You have to go through certification, you have to adhere to standards and all that, so it takes time. But hey, now they have a great product that's based on one of those platforms.
All right, that makes sense. Oh.
So two things. First, you had mentioned some, I guess, a software product that you use to translate software written in multiple languages to some standard language. Was it Swift or?
SWIG, S-W-I-G, Simple
SWIG.
Wrapper and Interface Generator. I think that actually started out as a Google summer camp project, you know, put together by students. But as you know, students usually are really hard workers. So it's good. You can actually take C++ code, turn it into Java. Sure, you'll have some problems because, you know, inheritance doesn't exactly quite work the same in both languages, but there are ways to get around it. And the projects are getting better every day, or that particular project is. They're on their 4th major release now. And they support not just the main languages, but also like, you know, things like Go, Lua, and I think some of those statistical languages too, like things like R. Yeah.
And then the second question was, you talked about standards earlier in your talk. One I didn't see mentioned was MUD. Are you familiar with MUD, Manufacturer's Usage Description? And
I am not familiar with MUD. There were actually a couple more that I had on that list. We looked at HID, Human Interface Devices. That's from Microsoft, right? And Microsoft was really good at defining standards. And you all know, like the drivers that came with Windows, you would get like 2 gigs of of your Windows installation would just be the drivers alone for all these devices that you have, right? They did a really good job, but like for Linux, it doesn't really apply as well. MUD, as I said, not familiar with it. There was one other that we looked at, Project Haystack as well. And then the ones that I had on the slide, but yeah. Another good one would be IIO there, because that's kind of like in the Linux space, right? And that's industrial I/O. It's baked into the kernel now and lets you access various sensors and actuators. And then these projects, MRAA actually does provide some abstraction for IIO too, so it makes it easier for you to use some of those devices.
No more questions? All right, so thank you very much.